dot should be written like f dot product with this. Okay, this is important because you have to consider what is the definition of the velocity gradient, and that is it will be del ui over del x j. Then you will have e hat j, e hat I. Okay, in some textbooks you may see a different type of a definition of grad operator. Okay, those textbooks are in continuum mechanics, and what happens is then their definitions change a little bit, so their final expressions change a little bit, but eventually when you substitute all the components, the governing equations are the same. Okay, you have to understand that visualizing these tensors as matrices is our choice. Okay, it's our choice how we represent the data, that is our choice. We may choose to go in a column major fashion or a row major fashion. Okay, where we arrange things in columns first and then in rows or vice versa, but the idea is that whatever you choose should not affect your final result, and the same applies to here also. So if you have this as your velocity gradient, then when we go ahead and simple, and we know that the definition of our deformation gradient tensor is, let us say, okay. So when you take the dot products, then you will see that these and this basis and this basis will get contracted, and you will see that f dot del u basically gives you let's write it like, and when you take the dot product, so these guys are scalars, their order of multiplication doesn't matter, so you just club them together and then you're left with, and now this guy is delta ik, so you the replace the I and k accordingly. Actually this is L k, so this should be L k, so this gives you delta I L, so you can either make I as L or L as I. Okay, and then you should get the final expression that we had for f dot. All right, so getting this out of the way, resuming with our discussion on momentum equation. So what had we written in our last class? We had written that del by del t of rho u plus del dot of rho u tensor u minus f, this whole thing integrated over the deformed configuration gives us the traction vector ds, where this st is the surface of bt. Okay, this st is the surface of bt. Now while looking at this t, yes, because it's the definition, no, so it's del uk by del xl e hat l e hat k. Huh? No, 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 no. So this is Fij. So Fij definition is del xi over del xj e hat j e hat I. Okay. These indices are chosen based on these guys. I mean, that's just convention. Okay. There's no real hard and fast rule what you have to write. The only thing is that this is how I have defined Fi capital J. Okay, and this is how I have defined gradient. Remember, gradient was defined like E hat I del by del xi. So the basis vectors of gradient come first. The basis vectors of gradient come first. Okay, so that is why you say J and then I, and so here you have L then K. Okay, now while writing this, momentum equation, we had simplified that this traction vector T can be written. So, for an arbitrary tetrahedral element of fluid, we said that this is n vector. So, we said that T n can be written like sum T1 bar n1 plus T2 bar n2 plus T3 bar n3. Okay. Yeah. Dot product commutative. Yeah. So, yeah, dot product is commutative. So, dot product is commutative between vectors. A dot B is B dot A when A and B are vectors. But if A and B are tensors, one is a tensor, one is a vector, it is still a commutative relation, but you have to understand how that commutative uh, property holds, because if you are visualizing tensors as matrices, then it won't be commutative. Okay, if you multiply 3 by 3 matrix with a 3 by 1 matrix, you will get a 3 by 1. In the other way, you will get a transpose of it. Okay, so actually what I had written earlier in the class was grad u dot f. Okay, when you write grad u dot f, you will actually get a transpose of the whole result. Okay, so again, quantities and components won't change, but it's their representation may change. So, just to keep it consistent with the kind of representation that we are doing, I have fixed it to this. Okay, because if I have write grad u dot f, okay, then you will see that things don't really make a lot of sense if I define gradient like this. So, the problem happens here. Okay, what is the dot product of this basis and this basis? We don't know. That's where the problem starts appearing. Okay, so that is why this is how you need to write f dot. Yeah, so Ej Ei, if you are saying that I am going to define my gradient of velocity as del ui by del xj E hat I E hat j, then you are basically changing the definition of your Nabla operator, which is not a problem. As I said, in some continuum textbooks, continuum mechanics textbooks, that you may see that happen, that they will not define delta like this or del like this. Okay, but then you have to follow everything consistently. Okay, it's a matter of convention. Given this definition, I am going to follow throughout this course this definition and whatever results follow from this definition. Okay, what I had written earlier was inconsistent with this definition. What I had written earlier was consistent with the definition that you say, that let us say grad is defined as del by del x I of whatever vector times E hat I. Okay, had I defined my Nabla operator like this, then everything will make sense, because then this E hat L will also come later on. This will be E hat I dot E hat J, and you will get the same result. With that definition of Nabla, this is correct. With this definition of Nabla, this is correct. Okay, just work out what you get when you use this definition of Nabla. You will see what I am trying to say. So, this is our Tn vector. We had shown that the traction vector on a arbitrarily oriented surface looks something like this. Okay. Now, I had written this. So, Tn, from here I had said that I can write it as, so the ith component of this guy I can write as Tij Nj. Okay, where basically this Tij is the ith component of jth traction vector. Okay, it is the ith component of the jth traction vector. Okay, so when we write Tn like this, when we write Tn like this, and let us say we try to imagine how does the stress, how does this matrix, I am not saying anything about it being stressed for now. So, let us say how does this matrix look like. So, basically Tij is the ith component of jth vector. So, that means the column number. Okay. So, what does it mean? How are the vectors arranged? Are they arranged column wise or row wise? Hmm? How are these guys arranged? Are they arranged column wise or row wise? Column wise, right? So, you have T1, T2, T3, okay, where each of them is a column vector. Do you see this? So, if this was T, so these are 3 components of T1, 3 components of T2, 3 components of T3. So, basically Tn is giving you, so Tn is okay, and you will get this T vector. So, that means this T I can write as this T I can write as so this is a this is a unit vector. So, so this means these are vectors. Okay. So, T1, T2 and T3 I had defined as traction vectors on the faces which have minus E1, minus E2 and minus E3 as normals. So, the over bar means that T1, this means it is this guy. Okay, that is all. So, I just defined this as a new variable where I am absorbing the minus sign. Okay. So, just look at this carefully. Okay, that I have written this T as this. So, when you write this guy T I j n j d s, we know from Gauss divergence theorem that this is actually going to be del by del x j T I j d v. Okay. This is actually going to be del by del x j T I j d v. Sure. Okay. How can I write this using divergence of this tensor? How can I write this? Let us say this tensor is T I j e hat I e hat j. Okay. Let us say the tensor is T I j e hat I e hat j. Then what is this expression? Is it this or is it this where this is transpose? Which one is it? Look at the definition of nabla that we are using in this course and tell me which one is it. Karo bhai, quickly. Someone must do the algebra. So, which one is it, del dot T or del dot T transpose? So if we have nabla defined like this, so we have ei del by del xi, let's say t, let's say what is del dot ti, del dot t. So this is t k l e hat k e hat l. So this gives us del t k l over del xi e hat I dot e hat k e hat l. This gives us delta I k. So this is del t I l over del xi e hat l. So the opposite one is going to be what? E hat I del by del xi t. So how is the transpose defined? So t, if this is t, then T transpose is basically T I j E hat j E hat I. So del by del xi T k l E hat l E hat k. Okay, so this gives us E hat I dot E hat l times E hat k. So this is del T k I over. So which one is it visible till here? Okay, so this is homework. I mean, this is basically me following this derivation with KL as same here, but EL EK instead of EK EL. Okay. Huh? Yeah, del IL won't be here because I've already swapped I and L. So that means the second index is the same here. Second index is the same here. So this guy is actually del dot of T transpose dV. Oh, इतना सा भी स्टेप ना लिखना ना पड़ता है यार. I mean, you guys don't have to click photos. I'm anyways sharing the notes, so that's moot. So you see, this is what we get, and now we have managed to convert this surface integral into a volume integral, and we can proceed with our usual logic, which is that this holds, this holds for an arbitrary deformed configuration. So the integrand must be 0, and that means okay, that means this is our momentum equation. Okay, this is often called the Navier's equation because there are some assumptions which were made by Stokes to get Navier-Stokes from here, but this is the general momentum equation that we are going to deal with. So let us just visualize what is each term in index notation first, and then we'll move on to writing more things about this T. So how does this look like in the index notation? Let's just write the components. Let's forget about the basis vectors and so on. Or let's write the basis vectors so that you guys get through the practice. So this is simply this guy. What is this? Let's say, so let's write something like this. Okay, equals Fi E hat I plus, so we know what is this going to give us, del T I j over del x j E hat I. So let us just look at this term. What does this term give us? So this is E hat k dot with E hat I E hat j, and then we have del by del x k of rho u I u j. So k and I will get swapped. So this is basically del by del x I rho u I u j E hat j, which I can also write as del by del x j rho u j u I E hat I. Okay. So, in the index notation, the components look like del by del t of rho u I plus del by del x j rho u I u j equals f I plus del t I j by del x j. In a few minutes, you will see that I made this whole big deal of this being del dot t or del dot t transpose, but it turns out that t is symmetric, so it does not matter. Okay. So, even if you do all of this algebra and try to make it very rigorous, physics is there for you and it will tell you that t is symmetric, so do not bother. But we will have to show that this t is symmetric. By the way, this t is called, I did not give it a name, this is called Cauchy's stress tensor or just stress tensor. And a lot of research in fluid mechanics is also about what this T should be. For example, for different fluids, this T behaves differently. For example, all of you might have seen those famous videos of a guy hitting oobleck, which is basically cornstarch and water mixture. Okay, cornstarch water slurry. If you hit it, it basically behaves like a solid, but if you slowly dip your hand in it, it's like a fluid. Okay, so that's a very classic example of a non-Newtonian fluid. What is Newtonian, non-Newtonian? Basically, you can derive the intuition from solid mechanics. What is a Hookean solid? When we say that stress is proportional to strain. What is a Newtonian fluid? When we say stress is proportional to strain rate. Okay, so it's the easiest type of fluid to model, that is the Newtonian fluid, and there are examples of non-Newtonian fluids as well. So, what is the difference in the governing equations of Newtonian and non-Newtonian fluids? It is basically this equation remains the same, this Tij will be different for different ones. Okay. Throughout this course, we are not going to look at non-Newtonian fluids. Honey is an example of non-Newtonian fluid, by the way. So, throughout this course, we are not going to look at non-Newtonian fluids. We may have some small problems on them, but we are not going to discuss in detail non-Newtonian fluids. We are going to focus only on Newtonian fluids. So, to see if this T is symmetric or not, actually we do not start with trying to prove that T is symmetric, we just write the next level of equation. So, in mechanics, once we look at linear momentum, the standard practice is to next look at the angular momentum. So, the usual practice is what we are going to follow. What we look at is the angular momentum equation. Now, when we are writing the angular momentum equation, basically Euler's second axiom for a blob of fluid, what we have to keep in mind is we are going to ignore any molecular spin and we are going to ignore any molecular moments. Okay, when I say molecular, you should think of it like on a fluid particle, because we are still discussing continuum mechanics. Okay, molecular does not necessarily mean molecules. What I mean by saying these two statements is that, let us say there is a fluid and there is a fluid particle, a very small fluid particle. Okay, even though it is small, it has some volume, it has some mass, so it is also going to have some moment of inertia. Okay, what I am saying is that basically there is no orientation change of this particle. When I say that there is no spin, okay, small fluid particles are not going to rotate about any axis in the space. Okay, so that means I am going to ignore any molecular spin, and similarly basically what I am saying is there are no moments that are being applied on small fluid particles. Okay, all the fluid particles, they don't experience any moments or any couples, to be precise. All the angular momentum and moment that you are going to generate is going to be due to this. So, the force is F dV. Okay, there is some force due to this guy. So, there is some force basically T dot N ds. Okay, and the moment generated due to these forces is all that we are going to consider about some origin O. Okay, there is some origin O and we are going to write. So, I am going to write this position vector is x. Okay, and the moment, the net external moments about O are basically the cross products of these forces only. So, they are simply x cross T dot N ds plus x cross F dV. This is the net external moment on a blob. So, this is your blob Bt, this is its original configuration. Okay. There is no magnetic moment or any other kind of a spin moment that is acting on the particle. And similarly, the angular momentum of the whole blob. So, this fluid particle is in the blob. Okay. So, angular momentum of this blob is simply x cross rho u dv. Okay. Now, substituting this in the Reynolds transport theorem to get the time rate of change. Okay. To get the time rate of change, we have to substitute it in the Reynolds transport theorem, and the final equation that we get is del by del t of x cross rho u plus del dot of rho u tensor product x cross u. Hold on, this is going to be yeah equals x cross f plus, and now we have that term. So, this is going to be x basically del dot of x cross t. This is how this term is going to simplify. Okay. It is easier to look at it in index notation, and that will be del by del t epsilon I j k x j rho u k plus del by del x L rho u L epsilon I j k x j u k equals epsilon I j k x j f k plus what you are going to get here is del by del x L epsilon I j k x j t. So, what do we write here? Actually, we have x j, so t k L. Okay. I encourage you guys to do the algebra for this. Okay. Anyways, I am going to give it in the notes, so I guess it's okay, but it will be good practice. Now, what we are going to do is I am going to take the cross product of the momentum equation with x and subtract from here. Okay. So, I am going to subtract from here epsilon I j k x j times the kth component of the momentum equation. Okay. So del by del T of rho UK plus del by del XL rho UK UL, and then equals epsilon ijk, that is already there, Fk plus del by del XL of TKL. So, I am going to subtract this equation by multiplying it with epsilon ijk xj. So, what do I get when I subtract these two terms? What do we get when I subtract these two terms? I mean, the question of why समझ नहीं आ रहा क्या चल रहा है? Is it clear till this equation or no? Huh? No, it's not clear. What is not clear? Where? This is this is this is moment. This is angular momentum. So, if this is your angular momentum, what is d by dt of HO? Here you will have to write the Reynolds transport theorem, right? Here we will have to use the Reynolds transport theorem, and your Euler's equation is this, right? All of this we are doing in a inertial frame, so I am not specifying if we are in the inertial reference frame or whatever. Okay, so I have written basically this. So when you compute d by dt of HO, you will have to apply Reynolds transport theorem. Is it clear now? So at least this equation is clear. Okay, you won't be able to get from this equation to this equation in an instant mentally without writing down it yourself. Okay, so the habit of converting your thoughts into some written word is very useful for doing this. Okay, so please do that practice, do a written practice to understand what is going on, to visualize how the index notation works from direct notation, and if you face issues you can always talk to me. Okay, so this to this you can work it out using index notation, and then what I am doing is I am subtracting the cross product of momentum equation taken with xj. So basically what I am doing is angular momentum, so angular momentum equation minus x cross linear momentum equation. This is what I am doing here. Okay, this is what I am doing here, angular momentum equation minus x cross linear momentum equation. Okay, so the first term epsilon ijk is constant, xj is not constant. What is del xj by del t? Basically velocity. Okay, so when you open up this product you will get epsilon ij k del by del t of xj, or rather let us write xj once outside, del by del t of rho uk plus rho uk del by del t of xj. Del by del t of xj is basically uj. So what is epsilon ijk rho uk uj going to be? Epsilon ijk rho uk uj 0, because rho uk uj is a symmetric tensor. Okay, so epsilon ijk rho uj uk uj is 0. In the direct notation you can think of it like taking cross product of velocity with itself, which is obviously 0. Okay, so this term with, after multiplying epsilon ijk, this term is 0, and then you are left with this term which is the same as this. So when you subtract this and this you get 0. What about these guys? So we have del by del xl of rho ul epsilon ijk xj uk minus epsilon ijk xj del by del xl rho uk ul. What do we get here? What is this? difference going to simplify as? So again let us see epsilon I j k is constant. So this is nothing but epsilon I j k del by del x L of the whole thing. Okay. So I am going to write using the product rule, I am going to write it as x j del by del x L rho u L u k plus rho u L u k del x j over del x L minus epsilon I j k x j del by del x L rho u k u L. So these terms cancel out and we are left with epsilon I j k rho u L u k del x j over del x L. What is del x j by del x L? Delta j L. So I can replace L with j. So this is nothing but epsilon I j k rho u j u k, which is what? 0. So this whole term is also 0. So on the LHS we have 0. When we have subtracted the angular momentum from the angular momentum equation, when I have subtracted x cross linear momentum equation, on the left hand side everything cancelled out. The force thing, the force term obviously cancels out. You can see it very clearly. This is also epsilon I j k x j f k. This is also epsilon I j k x j f k. Okay. The only thing that remains for now is del by del x L epsilon I j k x j t k L minus epsilon I j k x j del t k L over del x L, that is equal to 0. We got all the terms cancelling out. So this subtraction has to be equal to 0. Again applying the same, we have epsilon I j k x j del t k L by del x L plus t k L delta x j over delta x L minus epsilon I j k x j del t k L over del x L. So this guy cancels out and we get what do we get? So we get epsilon I j k x j, or rather epsilon I j k t k L delta j L equals 0, which means epsilon I j k t k j is 0, which means what? This means t k j equals t j k, which means T is a symmetric tensor. You can think of it visually like this. So this stress tensor that you are seeing in 2D, okay, the stress tensor that you are seeing in 2D looks exactly like what the stress tensor or the components of stress that you may have seen in solid mechanics course. It's just that instead of opposing rate, opposing strain, it is going to oppose strain rate now, but the components of stress look exactly like that. So this is, let us say, T11, this is, let us say, T22, this is T12, this is T21. Okay. Now for a small element to not be rotating, these guys have to be equal. For a small fluid element to not be rotating, these shear components have to be equal. Shear components are what? Off diagonal components. If off diagonal components are equal, T is a symmetric tensor. Okay. And that is essentially what is given by this maths that we have done, that the moment of our forces due to stress tensor is vanishing. Okay, moment, the net moment due to stress tensor forces is vanishing. So the stress tensor is a symmetric tensor. So it basically doesn't matter if you consider this or this in this course, it's both are same for the momentum equation. So now having shown that the stress tensor is symmetric, we can go back to the, so this is the whole discussion of angular momentum. Okay, this is, there's not going to be anything further that we can get from the angular momentum equation. This is all that we can get. Stress tensor is symmetric. Can you please again explain that shear force part, which you explained in the diagram? This you understand? That this is how we label the components. Huh? You understand this? Have you covered this in any solid mechanics course? मोहर सर्कल किया है, तो मोहर सर्कल में सिग्मा 1 1 सिग्मा 2 2 सिग्मा 1 2 क्या होते हैं? ये तो होता है. सिग्मा की जगह टी लिख रहा हूँ. दैट्स इट. सो द आइडिया इज, if this element, forget if it's solid or fluid, if this element is not supposed to be rotating, then the net moment has to balance. The net moment about center T11 and T2 do not contribute to any moment. They are just moments from this and this. So the idea is, if this is a square element, T12 has to be equal to T21. Extend this to 3D, all the moments in all directions should be 0. That will give you that the three components off diagonal in the stress tensor should be equal to the upper diagonal, lower diagonal, they should be equal. So basically stress tensor is symmetric. Stress tensor is symmetric when you don't expect a small element of the body to be rotating or to be resisting any moment. Okay, if you had, let us say, time varying magnetic field, time varying magnetic field on a charged body is known to apply a spin. Okay, or something like that. I am not an expert in electrodynamics, but basically if you have some magnetic or electrical spin that may be occurring on a body, okay, then you may end up getting that T12 is not equal to T21. Okay, basically when you are expecting a small fluid element or a solid element to resist any external moment, then it may appear that T12 is not equal to T21. But we are not going to consider anything like that in this course. Okay, that's a slightly more advanced thing to discuss. So now we are going to use this fact that T is symmetric, and we are going to try to model our momentum equation. We are going to model our momentum equation. Okay. So in the index notation, I can write this equation as del by del T of rho u I plus del by del x j rho u I u j equals del T I j by del x j plus f I. So this is in the index notation, and now we are going to attempt to model what is this T I j. So T I j equals T j I for any fluid satisfying these two assumptions. Further assumptions that we are going to make are, we are looking at a Newtonian and isotropic fluid. Okay, this is the simplest fluid that one can look at, And the reason why this is the simplest fluid one can look at is by virtue of saying this is Newtonian fluid, we say that Tij is proportional to the strain rate tensor. Which quantity is encapsulating the strain rate information? So far, whatever we have discussed in all the kinematics and whatever, what was that quantity which had strain rate information? Sij, which is the symmetric part of velocity gradient tensor. Let's not go to that specifics, although you are right. Let us just say velocity gradient tensor for now. That Tij is proportional to this guy. Okay. Why have I written different indices? Because there is no, it's not necessary that let us say a particular component of stress tensor is going to be dependent only on that particular component of the strain rate or the velocity gradient tensor. Okay. When you say that let us say two numbers are proportional, when you say x is proportional to y where x and y are scalars, then you put a scalar in front of them. But let us say I tell you, okay, two vectors are proportional, u vector is proportional to v vector, then what is the most general way of expressing this proportionality? Through a scalar or through a second order tensor? Because a second order tensor times a vector also gives us a vector. So the most general way of saying a proportionality between two vectors is to say, if I tell you that u is proportional to v, then what you should write as is u equals some second order tensor times v. So if you have two second order tensors, what is the most general way of saying proportionality between the two? Fourth order tensor. If you multiply a third order and second order, you will get a vector again. So the most general way is that Tij is actually Cijkl del uk over del xl. And this is the first and the last time when I am going to write a fourth order tensor on this board. Okay. I mean this discussion, it may happen that this gets stretched to next class. Yeah. So Newtonian fluid implies this. Okay. Saying that a fluid is Newtonian implies this. Saying that the fluid is isotropic as well tells us something about this Cijkl. Okay. And saying that the fluid is isotropic tells us that Cijkl is a fourth order isotropic tensor. Okay. Going back to our first or second lecture when we were looking at isotropic tensors, what is the second order isotropic tensor? Delta ij. Okay. A third order isotropic tensor is epsilon ijk. Fourth order, we had to build it using delta ij, delta kl combinations. Okay. And as it turns out, I can write this Cijkl as some lambda 1 delta ij delta kl plus some lambda 2 delta ik delta jl plus some lambda 3 delta il delta jk. Now since this guy is symmetric as well, remember Tij is Tji, so it's not just a fourth order isotropic tensor, it is symmetric in Ij as well. So for this expression to be symmetric in I and j, basically this to be equal to lambda 1 delta ji delta kl plus lambda 2 delta jk delta kl plus lambda 3 delta jl delta ik. What do you see? What should happen for this for these two to be equal? Right. So lambda 2 and lambda 3 should be equal. Only then these two expressions are equal. Okay. So, what we write this Tijkl as Cijkl as is Cijkl, we write it as a lambda delta ij delta kl plus some mu times delta ik delta jl plus delta il delta jk. Now, there is some constant which may be added to all of these Cijkls, okay, and the proportionality sign will still hold its value. So, basically the most general way of writing this proportionality sign is not just this, but some scalar constant times del u k by del x l as well. There is a fourth order tensor plus a scalar also possible. Okay. So, that means this Tij I am going to write as is C times del u k over del x l actually no wait, that can be absorbed in this C, no, that can be absorbed in this C ijkl. The most general way of writing this proportionality sign is by adding a constant with respect to kl. So, some constant times delta ij actually, my bad. Okay. So, this is constant, basically constant not changing with del u k and del x l. So, that is also proportionality sign where the proportionality constant is 0 basically. So, T I j is C times delta I j plus C I j k l delta u k over del x l, del u k by del x l, where C I j k l is given by that. Okay. We are going to simplify this in the next lecture.